Today, we're going to dive deep into a rule you probably learned on day 1 of chemistry class, the octet rule. We're going to explore why it's so incredibly useful and, more importantly, what happens when it breaks.
So, we all get taught that atoms want 8 electrons in their outer shell to be happy and stable. But is that really an unbreakable law of the universe? Or is it more of a really good guideline with some pretty important exceptions? Well, that's exactly what we're here to figure out.
All right, let's kick things off with a classic chemistry puzzle, one that comes up all the time when you're trying to picture what a molecule actually looks like.
You know, Lewis structures are fantastic. They're like little maps for the electrons in a molecule. But here's the thing. Sometimes, for the exact same molecule, you can draw a few different versions. And in every single one, all the atoms seem to be following the octet rule just fine.
This leads to a huge question, right? If you've got multiple options that all look good on paper, how in the world do you pick the one that's actually correct, the one that exists in the real world? Well, to do that, we need a special kind of tool, a way to do a little electron auditing.
And that tool, my friends, is called formal charge. It is absolutely key for being the tiebreaker between all those competing Lewis structures.
Okay, so what is formal charge? The best way to think about it is like a bookkeeping system for electrons. It's a pretend charge we give to each atom, and to figure it out, we make one big assumption, that any electrons in a bond are shared perfectly, 50-50, between the two atoms.
Now here's the official formula. I know, it might look a little intense at first glance, but trust me, the idea behind it is actually super simple. All we're really doing is comparing the electrons an atom is supposed to have with the number we've assigned to it in our drawing.
Let's just break it down into 3 easy steps. First, you look up the atom on the periodic table and see how many valence electrons it brings to the party. Then, you subtract all the electrons that are just sitting on that atom, not in a bond, the lone pairs. And finally, you subtract half of the electrons it's sharing in bonds. Whatever number is left over, well, that's your formal charge. Okay, theory is great, but let's actually put this tool to the test with a real molecule you've definitely heard of, ozone, also known as O3.
So here we have a pretty standard way to draw a Lewis structure for ozone. You'll notice we've numbered the 3 oxygen atoms just to make our lives a little easier. So let's get to it and calculate the formal charge on each one.
Let's start with that central oxygen, atom number 1. Okay, so a normal oxygen atom has 6 valence electrons. In our drawing here, it has 2 non-bonding electrons, and it's sharing 6 electrons in bonds. So we take 6 minus 2 minus half of 6, which gives us a formal charge of +1.
All right, moving on to atom number 2, the one with the double bond. It starts with its usual 6 valence electrons. From that, we're going to subtract its 4 non-bonding electrons, and then subtract half of its 4 bonding electrons. So 6 minus 4 minus 2 equals a nice stable 0.
And finally, we've got atom number 3, the one with the single bond. It starts with 6 valence electrons. We subtract its 6 non-bonding electrons, and then half of its 2 bonding electrons. The math is 6 minus 1, which gives us a formal charge of -1.
So here's the really important part. Even though the ozone molecule as a whole is neutral, our little calculation just revealed that there's a separation of charge inside the molecule. It shows us how positive and negative charges can be sitting on different atoms, all within a single neutral molecule. Pretty cool, right?
And this right here is why we do all this work. This is our guiding principle. It tells us that the most stable, most realistic, and most likely Lewis structure is the one where all the formal charges are as close to 0 as they can possibly be. It's how we pick the winner.
Okay, so now that we have this awesome tool for refining the octet rule, let's shift gears and look at the times when the rule itself just doesn't work at all. So our first exception is called the incomplete octet. And just like it sounds, this happens when the atom in the middle of a molecule is totally stable with fewer than 8 electrons in its outer shell.
Take beryllium in BH2, for instance. It's perfectly happy with just 4 electrons. And boron in BF3 is stable with only 6. For these guys, trying to force them to have a full octet would actually make the molecule less stable. It's a great reminder that chemistry has its own preferences.
Next up, we have the oddballs of the molecular world, odd electron molecules. You might also hear them called free radicals. With these, it's just mathematically impossible for every atom to have a full octet.
Think about nitric oxide, NO. It has a grand total of 11 valence electrons.
You just can't pair up an odd number of electrons to give every atom a neat set of 8. Someone is always going to be left out.
And for our last and probably most common exception, we have the expanded octet. This is where a central atom can not only have 8 electrons, but can actually hold more than 8. Now, this is only possible for elements in the third row of the periodic table or lower. The reason is they have access to something called d orbitals. Think of it like having extra closet space for electrons that smaller atoms just don't have. This lets phosphorus and PF5 hold 10 valence electrons, and sulfur and SF6 hold a whopping 12.
Whew, okay, that was a lot to cover. So let's just take a moment and wrap up with the key ideas we've talked about.
So, we've got formal charge, which is our go-to tool for picking the best molecular structure when we've got choices. And then we have our 3 big exceptions, the incomplete, odd electron, and expanded octets. Together, they remind us that the octet rule is a fantastic model, but it's not an absolute, unbreakable law. And this really leaves us with a bigger thought, doesn't it? When we find exceptions to a scientific rule, it doesn't mean the rule is wrong or useless, not at all. It means we're building a more detailed, more nuanced, and ultimately more accurate picture of how the world really works. It's a perfect example of science in action, a constant journey of refining our ideas to get closer to the truth.